Solving Cambridge Olevels Chemistry Paper 4 Alternative to Practical October-November 2025 and Paper 42. A student investigates the rate of a reaction. Figure 1.1 shows the apparatus the student uses. 50 cm cube of aqueous sodium thiosulfate is taken basically in a conical flask. Underneath there's a white paper on which a cross is drawn, and then there's a stop clock. Now what the student's going to do, the apparatus is quite simple, and we use this apparatus a lot in measuring the rate of the reaction. Actually what's going to happen is there's a reaction going to happen that's going to produce a white solid, and this black cross is going to be covered by that white solid or the powder that's going to settle at the bottom of the flask. And what that's going to cause is that's going to cause the solid solid is going to cause the black cross to disappear, and when the black cross disappears you stop the stop clock, and then you measure the time that it took for the black cross to disappear. State the name of the piece of the apparatus labeled A. So A is basically, you can see this is a cone shaped, right? This is a cone shaped. So that's why we have a special name for this flask. It's called the conical flask. Student adds a fixed volume and concentration of now the reaction is not started yet. You just have 50 cm cube of sodium thiosulfate. What's going to happen is that the student adds a fixed volume and concentration of dilute hydrochloric acid to A and swirls the mixture in A and places it back on the cross. So now the student has HCl. He's going to pour the HCl in here, and once he's poured the HCl in here, now the reaction is going to begin. So now the student is going to start the stop clock because the reaction is started. The mixture in the flask slowly turns cloudy. The student records the time taken for the solution to become so cloudy that the cross is no longer visible through the mixture. State the name of the piece of apparatus needed, which is not shown in figure 1.1. So the student adds a fixed volume and concentration of dilute hydrochloric acid. He is adding a fixed volume. To add a fixed volume, what kind of apparatus do you need? You need a measuring cylinder from which you're going to add the HCl into it. Okay? That's the thing that's happening over here. So we need a measuring cylinder to add our HCl. The student repeats the experiment with the same fixed volume and concentration of dilute hydrochloric acid with increasing concentrations of aqueous sodium thiosulfate using a new cross drawn on the paper for each experiment. So now what he's going to do is he's going to keep the HCl constant and increase the sodium thiosulfate concentration. Explain why drawing a new cross on the paper in each experiment reduces the accuracy of the result. Well, you can see it for yourself. The color may change of the crosses because what we're trying to do is we're just gonna look. If I draw two crosses and one of my cross looks like this, okay, and other cross of mine looks like this. Now you know that this cross is darker and this cross is lighter. So what's going to happen is this cross, this second one, is going to disappear more quickly. The first one, it may take longer than usual for the first one to disappear. So the accuracy of the results may be compromised, right? So we're going to say the color of the crosses might change. It may be darker or lighter. Crosses may be of different, you can say shades, not shades. We can say crosses may be darker or lighter. What this is gonna cause is it's gonna make the time differ, right? Which affects the time taken for them to disappear. This is a very famous rate question that's often tested. The student then uses the same cross drawn on paper repeats the experiment with the same fixed volume and concentration of dilute hydrochloric acid with increasing concentration of aqueous sodium thiosulfate. The thing that was in the flask was sodium thiosulfate, so that's going to be increased, but the HCl thing is not going to increase. Remember, suggest the effect of increasing the concentration of aqueous sodium thiosulfate on the time taken for the cross to become no longer visible. The time taken is going to reduce because now you have a more concentrated mixture, right? Over here, if you have concentrated sodium thiosulfate, what's going to happen? The rate of the reaction is going to increase because there are going to be more particles per unit time. More particles going to collide per unit time. So this is just knowing that increasing concentration increases rate. So the cloudiness is going to be formed quicker. Sulfur dioxide gas is produced during this reaction. Sulfur dioxide causes breathing difficulties in humans. It's just one precaution necessary when investigation to avoid breathing. Necessary in this investigation to avoid breathing difficulties. Okay, so basically, over here, what we can do is that there is a piece of apparatus that's called a quenching bath. And when in A levels you perform this experiment, you use the quenching bath to pour your mixture into it once the reaction is over. So you can use quenching bath, but this particular thing is not mentioned in the marking scheme. However, we do use it in the labs when we're working there and this SO2 gas is produced, but not mentioned in the marking scheme. I'd be very honest with you guys, what the examiner expects you to write is that we're using a place or an area which is well ventilated. I know that's very difficult to come in your mind, but that's the only answer that's mentioned in the marking scheme, that you have to use a well ventilated room or area where the air is like blowing so that the SO2 disappears. So that's what we're trying to do over here. What we're trying to achieve is that our sulfur dioxide gas, as soon as it is produced, it just like disappears. We don't want it to breathe, right? So that's why we want it to be blown away by the air. A student investigates the temperature changes when an acid neutralizes potassium hydroxide. We have the ionic equation which says H plus OH negative gives water. The reaction is exothermic. We're going to release heat. The temperature change is used to determine the concentration of the hydrogen ions in the acid. X is an acid of concentration 0.8 mole per dm cube. Y is 2 mole per dm cube potassium hydroxide. Don't forget that this is the most important. I would personally say just make a box around it. This is the most important piece of information that we're going to use. You know why? Because it's going to help us calculate out the moles. Step 1, fill the burette with Y. So we have this burette and we're going to fill it with Y. What is Y? What is Y? Potassium hydroxide. I'm going to fill my burette with potassium hydroxide. And then next step says stand a plastic cup inside a beaker. So what they're trying to say is, I'm going to show you this apparatus. It's a really cool apparatus that you have a beaker like this, and in that beaker you basically place a thermopole cup, something like this. Okay, so that's the apparatus, a beaker that has a thermopole cup, that white what do you call it, polystyrene or whatever, that polystyrene cup is placed in the beaker. Or you can use a plastic cup, that's also plastic. Uses a volumetric pipette. So now over here we're trying to be accurate and precise. Uses a volumetric pipette to put 25 cm cube of X. What is X? X is our acid. So now he is putting the acid which has 25 cm cube volume into the plastic cup, measures the initial temperature of X and records it in the table. So what kind of apparatus do you think is going to use to measure the temperature? He's going to use a thermometer. So going to measure the initial temperature and then adds 5 cm cube of Y from the burette into the plastic cup. So now we're going to be starting with a reaction. We're doing a neutralization reaction. We're going to place the burette, we're going to clamp it above it, And our burette has what kind of thing? It has potassium hydroxide in it. And then we're going to pour it dropwise, like 5 centimeter cube at a time, into the plastic cup, stirs the mixture for 30 seconds, records in table 2.1 the temperature of the mixture, repeats step 5 to 6 until the total 40 cm cube of Y is added. So first he's going to do it 8 times, like 5 in the first step, then going to stir, record the temperature, then 5 in the next step. He's going to add 5 cm cube from the burette in the next, then 5, then 5, then 5, and like this he's going to do it 8 times. 8 times 5 is going to make a total of 40 cm cube volume of KOH that's going to be added into this 25 cm cube of acid. On 2.1 on page 6 shows thermometer readings in degrees Celsius during the experiment. Complete table 2.1, record the students' result for 10 cm cube and 35 cm cube. Subtract the initial temperature of X from each experiment recorded to determine the temperature change. All the temperature changes should be recorded to plus minus 0.5. Do you know what this plus minus 0.5 means? Now people are going to ignore it straight away. I know what they're going to do. They've mentioned it. They're going to write 21 degrees. No. Plus minus 0.5 means you have to write 21.0 degrees. You can write 21.5 degrees. That's what plus minus 0.5 means. You can write it like this. You have to write it to 3 decimal place. Even if you write 21.00 and trying to increase the precision of your instrument, that's going to be wrong, because your thermometer doesn't measure up to 2 decimal places. It only measures like this. So you got to be careful about what you're doing, okay? Over here, the reading is 20, 21, 22, 23, 24, 25, 26. So this is 26.0, not 26 only. That's going to be wrong. I'm again, warning you. 20, 21, 22, 23, 24, 25, 26, 27. This is 27.5 degrees Celsius. Okay? Okay, 26.0 degrees Celsius, 27.5 degrees Celsius. And even if someone tries to be, very smart and tries to do some things that are not like appreciable, he's gonna see that all the readings already in the table, they're up to like 1 decimal place. So you also have to write it up to 1 decimal place. Now what are we gonna do? Volume of Y. अब now प्लीज़ डोंट ट्राई टू दिस कि आप इसमें से इसको सब्ट्रैक्ट करें. ऐसा आपने कुछ नहीं करना. आपका इनिशियल टेम्परेचर पता है. आपका जो इनिशियल टेम्परेचर वो है 20.5. ठीक है. जब आपने यू पुट द थर्मोमीटर फॉर द फर्स्ट टाइम इनटू योर plastic cup, the temperature is coming out to be 20.5. Okay, so now this is your initial temperature. Okay, and now you have to subtract all your temperatures for the temperature change from your initial temperature. So over here, for this column, it's going to be 23.5 minus 20.5. 23.5 minus 20.5. And that gives me 3 degrees. But I'm not going to write 3 degrees. That's going to be incorrect. I'm going to write 3.0 degrees. Now what I'm going to do, I'm subtract 20.5 and 26.0. That gives me 5.5 degrees. 29.5 minus 20.5, 9.0 degrees. 31.5 minus 20.5, 11.0 degrees. 30.5, now you're going to see a trend in the readings as well. 10.0 degrees. 29.0 minus 20.5, that gives me 8.5. 27.5 minus 20.5, that gives me 7.0 degrees. 26.5 minus 20.5, that gives me 6.0 degrees. Done with the table? Now I have to plot a graph of the temperature change on y-axis. So basically my y-axis, I should label it as Labeling is very important. Remember for graphs. Temperature change. Now you're gonna see something very beautiful about the neutralization curves. What's gonna be the beauty? Once I'm gonna plot the points, I'm gonna show you. There's a pattern to it that's gonna be something like this, from which we're gonna determine something. So there's like the entire beauty to it. And now we have to choose a scale for the temperature change. If someone plots the temperature, they are gone. Okay, they have messed up. You have to plot the temperature change. So our highest value is coming out to be 11 and our lowest value is 0. So we have to start from, I guess, 0, 1, 2, 3, 4, 5, 6. No, that's not going to work. 0, 0. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's gonna be 11, 12. That's how we do it. 0, 2, 4, 6, 8, 10, 12. And now we start with the work. For volume of y, that is 0, our temperature change is also 0. So I'm gonna plot this graph in front of you to make you guys realize that these 5 marks, I don't want any one of you to lose. That's simple as, I don't want to just say anything, but that's so simple that you just have to label this. You have to write the units. You have to do these small things to impress the examiner. So first point is on 0, 0. Second point is on 5, 3. Okay. So 5 is the volume that's added and 3 is the temperature increase. Third point is on 10, 5.5. 10, 5 and then 0.5. Don't try to be casual with it, thinking that no matter if I plot a point above or below the examiner, how is like a fool and not gonna notice. You're gonna be, once there was this examiner's workshop, and apparently a student had made a graph that seemed to fulfill 50% of the graph. Okay, they have a requirement, I don't know, whatever. And then some teachers complained, like they said, it seems like 50% of the graph is done. Why have you cut 1 mark? Then examiner took a ruler. Bro, he placed a ruler here and showed all the teachers that no, it's not 50%. It may be 48%. It may be 49%. It's not 50%. That's how precise he's about your graphs. Okay. 10, 5.5, 15, 9. 20, 11. 25, 10. 30, 8.5. 35, 7. 40, 6.0. Now I told you the graph is going to show you a pattern, an increasing and a decreasing. Now you're going to draw 2 lines of best fit. I know what they're going to say. Find the point on the graph where the 2 lines crosses. You have to draw 1 line of best fit for the increasing gradient. That's going to be something like this, I think. Should cover your maximum points. That's for my increasing gradient. And the second line I'm going to draw is for my decreasing gradient. Something like this. Now, the point determine the volume of y at this point. 20. 20 is the volume of y where my 2 lines are crossing. Okay? So, I'm going to write 20. Not 20. Yeah, it's fine if you write 20. But if you add a 0, What are we taking y with? Okay, it's fine if you write 20. Here it's fine. Y is 2 mole. Up now they're telling you again, it's 2 mole potassium hydroxide. The formula of potassium hydroxide is KOH. Calculate the number of moles of hydroxide ions in the volume of Y in C. First things first, you first need to calculate the moles of potassium hydroxide, and then you're gonna see what to do with these hydroxide ions. So for the moles of KOH, I guess it's pretty simple. You have the volume, that was 20 from the graph, 20, but we have to take it in like dm cube, so 20 divided by 1000 multiplied by the concentration, that's 2.0. So the moles of KOH come out to be 0.04 moles. Good. We have the moles of KOH. Now, the second thing that we need to figure out is that if we have the moles of KOH, what do we know about the moles of hydroxide ions? Look, if you have 1 mole of KOH and you're trying to dissociate it, you're going to form 1 mole of K plus and 1 mole of hydroxide. Tell me if I'm wrong. No. So from 1 mole of KOH, you form 1 mole of hydroxide. So from 0.04 moles of KOH, you're going to form 0.04 moles of potassium of hydroxide and 0.04 moles of potassium ion as well. Got it? The volume of Y in C, that's 20, is the volume needed to completely neutralize the 25 cm cube of X. Use your answer to D to calculate the concentration of the hydrogen ions in X. So they're saying that we use 20 cm cube, which was 0.04 moles of hydroxide ions to neutralize this H plus that was in 25 cm cube. Now you know that 1 mole of this is going to react with 1 mole of this. So how many moles of H plus ions are going to react? If we have 0.04 moles of hydroxide ions, obviously 0.04 moles of H plus ions are going to react. So the moles of H plus, because of the equation ratio 1:1, I know moles of H plus equals to 0.04. Now I have the volume of H plus because I know that I was using 25 cm cube of X. And what was X? X was HCl. HCl contains H. So I have 25 cm cube of H. I have the volume, I have the moles. What kind of formula I'm going to use? Concentration equals to my moles divided by my volume. Now I know that my moles are 0.04 and my volume is 25 upon 1000. 1, 2, 3, 0.025. Now let's see what is the concentration that we get. 0.04 divided by 0.025. Nah. Just messed up with the 0. I'm getting 1.6 moles per dm cube. So now we have some very common questions that the examiner is going to ask you in every exam, that why 25 cm cube of X is measured using a volumetric pipette and not a measuring cylinder. You just have to tell him what's more accurate. A pipette is going to be more accurate than a measuring cylinder. You just have to learn this line. So just why the mixture is stirred in step 6. Why do you stir a mixture? To allow the reactants to react. There's no rocket science in stirring the mixture. You just do it to allow reactants to properly mix or react and properly mixed together. That's the thing. Okay, so now we have a flame test. Student does a series of tests using aqueous solution of P and aqueous solution of Q. They test the student does in P are shown in table 3.1. Some of the observations for these tests are shown. So test number 1 is a flame test, and we have an orange red flame. Add aqueous ammonia, an observation we have to write. But they are not asking us, right? Some of the observation tests are shown. Okay. Describe how the student does a flame test. There's a very simple method of doing a flame test. Let me tell it to you. What you do is you take a nichrome wire, that's basically called a nichrome wire. You dip it into the solution whose flame test you want to do. So if I want to do a flame test for this solution, I'm going to dip my nichrome wire into this solution. And then I'm going to take out my nichrome wire from this solution and place my nichrome wire on a roaring blue Bunsen burner flame, something like this. And then I'm gonna have a flame color on this flame. Simple. Dip your wire here, take it out, place it on flame, and you get a flame color. Isn't it simple? You just have to now tell the examiner, but there's one thing about this flame. This flame has to be a roaring blue Bunsen burner non-luminous flame. Okay, that's what we call this flame. So the first step is dip a wire into this solution, and then place the wire on a roaring, you call it a roaring blue, I'm going to explain you what this means, Bunsen burner flame. There are two kinds of flame. One's a non-luminous flame and one's a luminous flame. So this one right here is a non-luminous flame. A luminous flame and a non-luminous flame, they have a little bit of color difference. So you might see sometimes you put fire and that's yellow in color, and sometimes you're going to see fire is blue in color. The yellow fire is basically your luminous flame and the blue fire is your non-luminous flame. For the flame test, you're always going to use non-luminous flame, and the reason for that simple. It's more hot and it's more appropriate. The yellow one's not hot enough. Describe one observation expected in test 2 based on observation in test 1. Test 1, we know that we're getting orange red flame. So you're going to go to the table below and we're going to see that we get orange red color for calcium. So if we know that there's calcium present in it, we're going to go to the sheet and see that if we add ammonia to our calcium, we're going to get no precipitates. Okay, so in the table, we're going to write no precipitates. Do we have to describe it below? Okay, write it here that we have no precipitates. No precipitates seen. Describe one additional test to confirm the identity of the cation in P. Include the test of a positive result. We have 3 tests. We have a flame test, we add aqueous ammonia, and the third thing we add is aqueous sodium hydroxide. Okay, so aqueous sodium hydroxide, aqueous ammonia. From ammonia we get no precipitate, a very slight white PPT, and for calcium we get white PPT that's going to be insoluble in excess for sodium hydroxide. So over here we're going to write white PPT that's insoluble in excess. So test is going to be we add NaOH aqueous, and the result is going to be white. Please write the full thing. I'm just doing it because like I'm not writing a Cambridge exam. White precipitates, first NaOH drop wise and then in excess, and then in excess white precipitates forms that is insoluble. The word insoluble is important here. In excess. And now they're asking us to identify the cation that's a Ca2 plus ion. Solution Q is acidic the test, that means it contains H plus ions. The test the student does when Q is shown. Some of the observations of these tests are also shown. Add 5 drops of universal indicator, and then you're going to see a color change. Add a piece of magnesium ribbon, and you're going to see the magnesium ribbon disappear because hydrogen gas is going to be formed here because we are dealing with an acid, and then we add a metal to it. So we're going to see hydrogen gas. Next step, add dilute nitric acid followed by aqueous barium nitrate. So we're going to form a white precipitate, and the white precipitate is going to be of barium sulfate. Describe the expected color change in test 3. At 5 drops of universal indicator into an acid, it turns red. You know, universal indicator is red in acid and blue in alkali. So that's the thing. From green, it's going to turn to red. A gas is produced in test 4. We know hydrogen gas is produced because we're dealing with magnesium and a metal, which is a metal with an acid. So an acid plus metal is going to give hydrogen. Predict the identity of the gas produced in test 4. Okay. Describe a test to confirm the identity of the gas. Include a result of the positive test. So you know that the test for your hydrogen gas is that you use a lighted splint. And then you know it extinguishes with a pop sound. Q contains 1 cation and 1 anion. Identify the cation and the anion in Q. अच्छा जी, अब Q में anion और cation identify करना है. Cation and anion. Cation तो hydrogen ion होएगा because ये acid है. And the anion. Did they tell any other test for Q? It's acidic and it's dilute nitric acid followed by barium nitrate is forming barium sulfate. So the anion is the sulfate ion. That is sulfuric acid. The reaction between a metal and dilute sulfuric acid is exothermic. Exothermic reaction means that it is going to release heat energy. Plan an experiment to determine which metal. We're given with 3 metals. Magnesium, zinc. We're given with 2 metals. Magnesium or zinc releases more thermal energy per gram. So over here the important word is per gram of the metal when reacting with excess dilute sulfuric acid. You are provided with magnesium powder, zinc powder, dilute sulfuric acid and common laboratory apparatus. No other chemical should be used. Your plan should include. अच्छा, अब मैं आपको I'm going to tell you something that's worth listening to. And that thing is, you know, the marks. People often get confused. How do you get a 6 on 6 on this question? What's the tip? What's the trick? And you know, because it's been recently added, so many people struggle with this thing. But it's as easy as ABC. Why is it as easy as ABC? Because look, the marks in your marking scheme are going to be given if you correctly address to the 3 points provided. If you tell the apparatus you use, and then you tell the method you're going to use, and then you tell that how the method is going to determine which metal releases more energy per gram, you're going to get your mark. So over here, I'm going to plan my investigation in front of you. Basically, I just don't write first. I go to the last page where I have this area, this blank area, and I start drawing over there. And then I realize what I'm going to do. So if I were in a laboratory and I had to determine this, what I would first do is, I would, obviously because I'm doing a heat experiment, first what I'll do, I'm going to tell you my thought process. I'm going to take a measuring cylinder and I'm going to measure a fixed amount of H2SO4, which is sulfuric acid. And then I'm going to pour the sulfuric acid into a beaker. So I'm naming the apparatus in front of you, so you guys are not confused. After pouring my sulfuric acid into the beaker, I'm going to add my piece of, I had zinc and magnesium. So I'm going to add my piece of zinc into my beaker. But over here, there's an important thing. I need to have a fixed mass of zinc. Because look, I need to measure the energy change per gram, right? So for that, I'm going to use fixed mass of zinc and fixed mass of, what do you call it? What's that thing? What do you call it? What is that one thing that's called measuring balance? Yeah, measuring balance. So you're going to measure it with that measuring balance thing. Okay, so I'm going to measure the mass of this zinc. So that's how I'm going to address it with a measuring balance. Now, before adding zinc, I'm going to make sure, since I'm doing a heat experiment, I have to measure the initial and the final temperature so that later I can get the temperature increase. So I'm first going to measure the initial temperature using a thermometer, and then after adding zinc as well, I'm going to measure the final temperature. So after adding my zinc, I'm going to make sure my sulfuric acid is in excess. So all my zinc is going to react. Now I'm going to measure the final temperature on the thermometer. Once I've measured the final temperature of the thermometer, there's an equation that we use, that is Q equals to mc delta T. Q is the amount of energy released, M is the mass of the solution, right? And C is the specific heat capacity of water, which is 4.18. M is the mass of the solution that we're going to use. That's going to be the mass of the sulfuric acid we're taking. And T is going to be the increase in temperature. This equation I'm going to use to calculate the amount of heat energy that's going to be reduced in this reaction. Okay? And important thing over here is that I'm adding a metal to an acid. Zinc or magnesium is a metal, and I'm adding a metal to an acid. So there is going to be bubbles and effervescence. So one important thing over here which I can think of, that I'm going to measure the final temperature when my bubbles are over, because I know that the reaction is complete at that time. Okay, so I'm going to make sure my reaction is finished. Now I have to, whatever I've just thought of, and then what I'm going to do is that amount of energy change for the metal that I get most energy change is going to be the one that's going to release obviously more energy per gram, because I've taken equal masses of zinc and magnesium. I'm going to do this with zinc first, and then I'm going to repeat the same procedure using the same volume of sulfuric acid, same mass of the metal. I'm going to again do this experiment, and then I'm going to, in my equation, I'm going to, instead of T, delta T is going to be different for obviously magnesium because it's a different metal, but I'm going to otherwise take everything as same. Do you get it, what I'm trying to do over here? So that's the kind of experiment I do. So now I'm going to write my answer by addressing all the points. So first point is the apparatus needed. According to my working, what kind of apparatus I'm using? First, I'm using a measuring cylinder to measure the fixed volume of sulfuric acid. Secondly, I'm using a beaker for my reaction to proceed. Thirdly, I'm using a thermometer. And fourthly, I'm using a measuring balance to measure the fixed mass, because over here we are dealing with the amount of energy released per gram. Per gram means that 1 gram. Okay, so you got to have fixed mass of both of them. That's what you got to make sure. So if I address the points, I know I'm going to get my marks. The first mark is going to be awarded if I write the correct apparatus. Okay, my apparatus is going to be a measuring cylinder, because I need the fixed volume of my acid every time. Second thing, I need a beaker to carry my reaction. Third thing, I need a thermometer to measure my temperature increase, initial minus final temperature. The fourth thing that I need is gonna be a measuring balance. What do you call it? Measuring balance or only balance? I think you only call it a balance, not a measuring balance, and a balance. So that's my apparatus. I'm given the marks for the apparatus. And mind you guys, there are 3 marks you can get: M1 mark, M2 mark, and M3 mark just for writing the apparatus. So please don't think it's useless. If you miss out these points, you're not going to get the marks. Second thing, now I'm going to describe my method. Okay, my method is that second thing I'm going to address to the method. You don't have to give these headings, I'm just giving it to make sure that you know how the marks are broken down. Okay, the method is you have a lot of space. Look, I don't know how many lines are these, but there are a lot of lines. So you can just write whatever like you feel like writing, the entire method. Take a fixed volume of H2SO4 using a measuring cylinder and pour it into a beaker, and then add a fixed mass of zinc. No, first you have to record the initial temperature and then you have to add zinc. So you got to make sure that you're writing it in correct order. Measure the initial temperature initial, and then add a fixed mass of zinc. Allow the reaction to proceed. Allow the effervescence, because you're going to produce hydrogen gas, to stop, and then measure the final temperature, okay, of the mixture. Repeat the same steps with magnesium. The second metal was magnesium now. Magnesium, by taking the same volume of H2SO4 and same mass of Mg. Okay, now you're gonna measure the temperature now by using the formula Q equals to mc delta T, where m is the, I'm gonna write everything, I don't want my marks to be cut off, okay? Where m is the mass of the solution, C is the specific heat capacity of water, and delta T is the change in temperature. Find the heat energy released for both metals. Done. Second point, method, I've described it in my own words. I know it was a little lengthy, but I don't care about the length as long as I'm writing everything that needs to be there according to me. Third point I need to address now, how the measurements are used to determine which metal releases more thermal energy per gram. So I need to determine that which metal is going to release more thermal energy. The metal which is going to have a greater change in temperature. Because look, I was using the formula mc delta T, right? M is the mass of the solution. I told you I'm going to take fixed mass of the volume of the mass and volume of the sulfuric acid and fixed mass of the metal. So mass of the solution is fixed. C is the specific heat capacity of water, which is 4.18. It is fixed. So the amount of your Q, which is the amount of energy released, is going to be dependent on the temperature change. So the metal which has the largest temperature change is going to have a greater energy released per gram. So that's simple. So the third step is determining which metal releases more energy, okay? So now, according to me, the metal for which there is a greater energy, not great energy change, greater temperature change releases more energy per gram. That's how I'm gonna determine it. And we're done and dusted with this paper.